Welcome back after the lunch. We hope you're feeling refreshed now to begin our afternoon program. Now we have our next thematic session on thematic area 5, biodiversity, urbanization, and sustainable resource management. In this session, we will examine strategies for conserving biodiversity, managing urbanization impacts, and promoting sustainable resource use in Bhutan and the Himalayas. The session will touch on innovative approaches such as eDNA monitoring, mycelium-based materials, and riparian ecosystems, alongside waste and energy solutions, including biogas and wastewater resource recovery, and thereby emphasizing evidence-based practices for resilient, sustainable, and ecologically balanced communities. To begin the session, we have the keynote speaker, Mr. Chimi Rinzin, Country Director of the World Wildlife Fund, WWF. Mr. Chimi works to advance conservation program and leadership in partnership with communities, CSOs, and NGOs. As the country director of WWF, he is passionate about environment and natural resource management, sustainable development, and climate change. He has more than 20 years of work experience with demonstrated leadership in organizational management and growth, policy, program, and portfolio development, resource mobilization, and execution with a clear focus on achieving results. Prior to joining the WWF Bhutan, he served as the portfolio specialist for climate change adaptation and disaster risk reduction at UNDP Bhutan. Let's welcome Mr. Chimi to present his keynote on the topic, Bridging Technology Gap for Effective and Inclusive Conservation.
Ambassador, Vice Chancellor, colleagues, students, good afternoon. Let me express, first of all, my sincere thanks to Royal University of Bhutan and organizing committee for this conference, for giving me an opportunity to speak, and I hope I can live up to the expectations of previous speakers and moderators. It is also wonderful to be among all of you, bright academic minds, emerging scholars, thought leaders from both the countries. And it's also a joy to be in this fraternity because I was once a graduate from Sydney University and I was pursuing agriculture degree. And when Dr. Mamta spoke about rust and wheat and all those things, I think it brought me back to memories of where she is now, Camden campus, doing research on agriculture. Although I had been given this privileged role of being a keynote speaker, I wanted to clarify that I would mostly be talking about scenarios and situations that would actually set context for what we are going to hear from our researchers. I think they should be the main focus and not necessarily my keynote speech. And of course, keeping in with the session's theme of biodiversity, urbanization, sustainable resource management, I wanted to reflect on the issue that is rapidly shaping our future of human development and hence how it's shaping our conservations. And my reflection starts with a very simple question, how can we leverage technology to bridge the gap of effective as in protecting the system that is protecting us, and inclusive conservation so that conservation has a human purpose. What does it mean for human development? What does it mean for human advancements? So those are some of the key questions that I sort of asked when I was given this topic. When we talk about effective and inclusive conservations through the medium of technology, it requires a paradigm shift, one where conservation serves as the core enabler and the foundation of sustainable and resilient human growth. And when I'm saying this, I'm also mindful because I represent Wild Wildlife Fund. And when people look at Wild Wildlife Fund, they usually see us through the lens of species. In Bhutan it is tiger, snow leopard, and in Australia it's like koala and other things. And sometimes this is a problem for us because people have such a narrow lens of looking at conservation. So, and sometimes people also see us as a partner of rangers who has a policing kind of a mindset. So when I talk about this topic, it's really about breaking that mindset and trying to come to a convergence where we talk about common things. Okay. So when we look at conservation challenges of today, I think it's much more complex. It is beyond protection, exclusion, and policing. That was how conservation evolved in the past. And we are living through a century of extraordinary transformations. This is the first case of what current transformations looks like and what are the ecological stress. First, we are witnessing unprecedented ecological stress, as you see here, rapid urbanization and population growth. 10 billion people by 2050. It's a huge amount of stress because of population growth. If you look at the biodiversity, we just have an accelerated decline of biodiversity populations around the world. 73% decline in monitored wildlife since 1970s. And if you look at climate change, we heard about climate change yesterday from Dr. Dan. 2024 was the hottest year ever recorded, surpassing the 1.5 degrees Celsius, which we, for the last 30 years, tried to stop. And we have now already crossed that tipping point. So this is a scenario that's in front of us. We are living through these challenges. Therefore, conservation today has to respond to this kind of disruptions, climate change, urban expansion, land use competitions, equity and inclusion, because we increasingly need to discuss about it. And more importantly, I think it's governance. And how do we bring people into a larger aspects of conservation. So therefore, it really requires us to ask the questions of why do we conserve? For whom do we conserve? And how do we conserve so that both nature and development can thrive together? The second changes that we are living through is, this is a century defined by astonishing technological progress and transformation. We heard about technologies this morning, we heard about technologies yesterday, and we are living in the space of how every facet of our life is influenced by technologies. Biotechnology, we heard this morning how it's influencing agriculture, information technologies, how it's shaping, and artificial intelligence, automation in data system that now allows us to observe, analyze, and deliver on imagination that was never possible just 10 years ago, even 10 years ago. So technology shapes nearly every facet of our life. The phones that we carry, the transport that we use, the algorithm that now write, respond, predict, and advise us, AI, ChatGPT, and so many other things. Yet, we often tend to forget the very technologies that we depend on depends on nature. The very forest, rivers, mineral, soils, and ecosystem quietly regulating our water, climate, food, air quality, and of course, helping us to see through the disasters. Look at the water that is in front of us. Sometimes we feel that this is just a water, but never try to associate or even think of associating the water that is in front of us has its origination in nature. So technology, guided by science, can bridge ecological integrity and human well-being, and thereby helping us to realign development pathways with the reality of ecosystem that is under pressure, as we are witnessing today. But for Bhutan, what does it mean? Let me just give you a typical scenarios that we are in. For Bhutan, we are in a very strategic paradox. On one hand, Bhutan shines globally as a beacon of environmental stewardship, leadership, 70% forest cover, 52 protected areas, our foremost carbon negative countries, and conservation that is deeply rooted in our ethos, culture, spiritual ethos. Yet Bhutan faces the same ecological pressure that the world is going through. While we heard yesterday during the fireside chat the ambition of where Bhutan wants to be 10 years from now. Look at DHI, from 1 billion company now they want to grow to 10 billion company. 21st century economic roadmap, it's the same stories, we want to achieve higher GDP. So in a sense, we are also sprinting towards achieving that goal. So under such economic aspirations and circumstances, I for one believe that conservation technology is not just useful for Bhutan, but it is a strategic options that we need to explore, adopt, and innovate. So it can help us sustain carbon neutral legacy, a commitment that we made to the global communities some years ago. Support the constitutional mandate of maintaining 60% forest cover, and it is a legal covenant as a nation that we signed through our constitutional process. And it can and should enable the ambition of 21st century economic roadmap, which is the aspiration of the people of Bhutan. And that's why we have GMC coming up. There are so many other economic approaches and model that we are seeing being experimented at the moment. But I think that brings us to our questions of where do we stand in terms of technology when we talk about conservations. I think we have made very good progress. There has been a deliberate sort of approach from the government side as well as from the conservation fraternity to adopt conservation. So you can see different types of technologies that are being deployed to help our decision makers on the ground, to help our farming communities on the ground, and at the same time help our policy makers at the national level to make that conscious decisions of how do we live through these challenging times. And latest one, which you will hear from our colleagues, we are talking about eDNA that serves as a new lens for biodiversity. So some of these tools are also helping us to discover new biodiversity assets, enabling build up inventories of Bhutan natural capital. And I believe that at some point, this should help us, just like carbon stock that we have, to deliver new revenue streams. So Bhutan's conservation journey has been extraordinary, but next chapter requires us to adopt adaptive stewardship, powered by science, enabled by technology, grounded in culture. I don't think we should never lose sight of that, and most importantly, centered on people. So with this, I would like to conclude here, and we'll hear more about different aspects of conservation technologies that are emerging, that has an industrial application opportunities as well. Thank you.
Thank you, Chimisa, for highlighting the need to embrace coexistence with innovative conservation technologies for ecology integrity. Now to move on to our first session speaker on this thematic area, we have Karma Sherab, lecturer at the College of Natural Resources, Royal University of Bhutan, who is currently pursuing his PhD at ETH Zurich, Switzerland in wildlife management. Karma's work focuses on developing effective strategies to mitigate human-wildlife conflict and also exploring the use of environmental DNA, or eDNA, as an innovative tool for large-scale wildlife monitoring. In his home college where he teaches, Karma focuses on integration of research and teaching to promote sustainable wildlife management practices, and his goal is to contribute to evidence-based conservation solutions that balances ecological integrity with human livelihoods. Let's welcome Karma Sherab to present on the topic, comparing watershed-based eDNA sampling and camera trapping for assessing mammal diversity in northwestern Bhutan.
Good afternoon to everyone. So I would like to introduce again. My name is Karma Sherab, and currently I'm pursuing PhD at ETH Zurich in Switzerland, and also I'm serving as a lecturer at College of Natural Resources. So over the past 3 years, I've been working with the eDNA to detect the wild animals. And this is the baseline study where we try to compare the detection from eDNA with the camera trapping. Just we wanted to see how sensitive is eDNA before rolling out like nationwide survey. So to give a little context of eDNA, eDNA is a tiny traces of DNA that is left in the environment by the organism. And that traces of DNA can be from saliva, from the hair, from the skin, or also from the feces. So all animals, they left those things in the environment. So in eDNA analysis, what we are doing is we are trying to capture those information and identify the species. So here, we don't have to capture, we don't have to see animals. So we are getting all the information from the environment. And for this eDNA sampling, we can sample from water, we can sample from soil also, we can, we can even swipe the leaves and all those things. But for insects, since they are constantly contacting with the leaves and all those things, it is effective for the insects. So if you want to study about the insects and all those things, you just suck the leaf and bring to the lab, and you will know all the insects that has visited these leaves. For other organisms like fish, reptiles, amphibian, and all those things, water is the best medium to sample the eDNA, because those organisms are constantly contacting with the water, and as you see this picture, the water is coming from different directions. So in all those spots, there are animals who are frequently contacting this water. So water is bringing all those information of the animal, of DNA. So we are capturing this, and in this research, like in Bhutan especially, we are using water as a medium to collect the information, to detect the species. So this is the machine that we are currently using, and it was developed by our group in the ETH. So this is a pump which pumps the water, and if you look at the white one, this is a capsule. So it pumps the water, goes through the capsule, and this is where the magic happens. All the DNA is left in the capsule. And then we take this capsule in the lab and extract the DNA, and then we do bioinformatic analysis to see what species are there. And we are also involving like local people to do the survey. So we are training them, we are letting them collect the eDNA sample by themselves so that they can play a part of a role in the conservation. And also, since they do it themselves, they can appreciate the existence of wild animal in their locality. So I'm still continuing with this work with the local people. So for this research, we piloted this research in Jimmy Doji National Park and the fringe area towards the south. So what we did was we divided the entire area into 6 watersheds. So the reason for dividing this into 6 watersheds is because we wanted to define the ecological unit for doing for eDNA sampling. Because for example, if I sample water from this Wangchu, from the Lungten Zampa, I will get snow leopard, and I will get also the tiger. But if I say, okay, since I get the snow leopard, if I say, okay, snow leopard is there in Dechinpu, then it's a wrong concept. So that's why we wanted to define an ecological unit, and the best ecological unit we found was the watershed, because there is no much variation. Since watershed is a small area, so there is no much variation in the habitat, and animal has no boundary except those snow leopard, some like yes, and also tiger, which sometimes go high altitude, but snow leopard doesn't come down until and unless the climate change affect all those areas. So, and also then we collected the camera trap which is having the species information from all those watersheds. And we collected the eDNA water sample from all those areas. Now we have information of the species existent from the camera trap, which is very much reliable. And then now we also have the information from the eDNA. So now I want to present a result, which is very fascinating. So this is the first part of the result. So from the eDNA, this is a Venn diagram. From the eDNA, we detected 60 animal species. And I'm using the term animal species, but these are mammals. So 60 animal species. And from the camera trap, we have detected 33 animal species. And the eDNA has detected like more than 85 species detected by the camera trap. And also, eDNA has detected 90% of threatened taxa. So that means you look at the magic of the eDNA. And for when we do a camera trapping, so we face a lot of logistic challenges. We have to work, with the rough terrain and all those things. And with eDNA, you just where you go to the river, just sample. You don't have to travel a long way. And we also try to fit a model. And the both model, it shows that eDNA is performing better. So this first model is built based on all the species. And the second model, we have deleted the small mammals. Because in camera trapping, we focus mainly on the medium and large mammals. So we wanted to see these differences. And the model was predicting eDNA is performing better. Oh, I'm very sorry. So maybe you can next measure to the manuscript. Offline. Then, because the eDNA should be very convincing before we adopt this in Bhutan. So that's why we have a second result. We try to check the detection probability of the species between the two methods. Detection probability means the chances to find the species. So the blue one is a eDNA, and the brown one are the camera trap. So if you look at this plot, you will see eDNA is having like higher detection probability than the camera trap. So even see, with eDNA, we are getting more number of species individual than the camera trapping. But only thing is, as I said, with eDNA, you will not see the animal, but with camera trap, you will see the animal. Then thirdly, I already said that we wanted to develop an ecological unit for the eDNA sampling. So this is the result of that one. So we plotted the taxa composition similarities. And all those purple color are having a similar taxa composition. And we applied this PCO result on the map. And you can see the higher altitude, Laya and Lingji site, they are having somehow similar color. That means they are having similar composition of taxa. And below is more purple. So they are having similar kind of color, similar kind of taxa composition. So this is how we can now say that the watershed is serving as an ecological unit for the eDNA sampling. And our achievement, and I'm very much proud to announce here, that through this project, we were able to develop eDNA lab in College of Natural Resources. And this is the first eDNA lab in Bhutan. And we are training the master student, and we successfully trained 2 of the master students, and they have analyzed their eDNA sample in College of Natural Resources. And one of the master students is here. He will be presenting next on the same topic. And also, together with ETH, we have initiated a global network. Right now, we have 20 partners who are working on eDNA, and we are sharing the information in a single platform, that is wildliving.org. And this platform, when we share the information, it gives us an index. And we want to survey with the eDNA every year. And the website automatically calculates into an index, like whether the species is declining or it is increasing. So that's all. Thank you very much.
Sorry for the technical glitch there. Thank you, Karma, for sharing your study of the environmental eDNA and camera trapping methods to study animal diversity in Bhutan's catchment area and through the watersheds. To move on to our next speaker, we have Mr. Jigmitile, who's a senior forestry officer with the Department of Forest and Park Services and undergoing his MSc in Conservation Biology at the College of Natural Resources and graduating in 2026 next year. He has served the Department of Forest and Park Services since 2011 and is currently with the Monga Forest Division. His thesis investigates mammal use of Biological Corridor 7, facing infrastructure and climate challenges, integrating camera traps, science surveys, environmental DNA, and human-wildlife conflict surveys. And the corridor focus eDNA component forms part of his thesis. Please welcome Jigmitile to present his work on environmental DNA in mammal species monitoring in biological corridors of Bhutan.
Yes, good afternoon all. So this is one component of our previous speaker, who is my master. So this is one small component from the overall eDNA project. So this study deals with connectivity analysis. Biological corridor is meant for the connectivity of animals from one protected area to another protected area. This is the topic. So the topic says environmental DNA in monitoring of mammals in biological corridors of Bhutan. So the background has been already said by previous speaker. So the little more context setting, like biological corridors like bridges for the transportation. The biological corridor serves as connectivity for the mammals to pass from its one home to another home. That's the purpose of biological corridor. So camera traps has been popular technique for monitoring of mammals. So eDNA is now evolving in our country with recent deployment. It was actually tested in Mangdechu River Basin. It is not actually a first, to be precise. It was tested in Mangdechu Basin with collaboration with ETH. And this eDNA technique, for now, it is being tested in one of the biological corridors of Bhutan. So there are 3 objectives for this work. First, assessing composition. Second, the assessing evaluating diversity, then they finally determining occupancy and detection probability of mammals in the corridor number 7. The significance is same actually to find out what are the species present in biological corridor number 7, then where are the more species located, and to again to check whether it complements with camera traps. And thirdly, it will also help in building national database. Fourth. And finally, it will be useful for policy making. This is the study area, biological corridor number 7, which connects Wangchuk Sentinel National Park in the north. Then in the west, it connects Phumsingla National Park, and in the east, Bomdiling Wildlife Sanctuary, that is in Tashiangtse. So data collection, it is the same principle that was already presented. Using that pump and filter, we collect the sample. Actually, I collected 14 samples, 2 replicates per site. From 7 tributaries, I have collected the data, which took only 4 days to collect the data. And the even riparian habitats data were collected. For laboratory analysis, 90% of laboratory analysis was done at College of Natural Resources with that eDNA lab, one which was launched recently. That lab was used to extract the DNA samples. The final part, sequencing part, was done at ETH University. And the data analysis was mainly done in R, and I also used Python a bit for something. This is the site information, and the sampling effort is just 4 days. And the main habitat was Chirpan and broadleaf forest. And this is the finding. So I got actually 35 species. Here I have missed, it is written 28. So among the species types, omnivore were dominant, and even carnivore species were also there. And our monkeys were dominant species, and we also got leopard and wild dog. And in categorization part, we got all kinds of species, including threatened species. And among 7 plots, we got highest 20 species in 2 plots, and the least was 7 species in one of the plots. These are the species. So richness, same thing. And about sampling coverage, this graph shows the sampling coverage was actually normal. So among the 7 plots, 2 plots were giving enough sampling coverage. So this is the kind of graph that shows common species and unique species. From the figure, 5 species belong to all the plots, and only 3 or one species were unique to 3 plots. And this is the detection probability. This graph actually shows the occupancy and the detection probability. Common species were they're having high occupancy, and detection probability was also high, whereas threatened species or rare species, they are having less occupancy, and detection probability was also low. And the interpretation of the results, camera trap data I have just used only in this slide just to make the comparison. eDNA is actually capturing more species within 4 days, taking only 2 hours per plot. We are getting all kinds of species. Whereas to get 26 species, I took 7 months to get this many species. Like carrying luggage and everything we have. Actually, we have to do both. One cannot replace other. I think from my side, I don't know about my group, but from my side, I think we should use both. practical implications, we have to complement with camera traps. eDNA actually shows what species are there. Camera traps will go there and get the images. Actually, they should go side by side. And I took only samples from one season. 2 seasons can be done to get the real picture of the ground. And the theoretical implications, it is just theoretical part, so I'm skipping. That's all. Thank you.
Thank you, Jigme, for sharing the findings of your species discovery through the eDNA and camera trapping methods, uncovering mammal species both common and rare, and also for the practical difficulties that you had to endure with your supervisor. To move on to the next, we have Dr. Sonam Tashi, Dean of Research and Industrial Linkages of the College of Natural Resources, Royal University of Bhutan. Dr. Sonam Tashi is an associate professor and the Dean of Research and Industrial Linkages.
Yeah, thank you.
He has also served as the Dean of Academic Affairs in the same college. Dr. Sonam holds a PhD in Agriculture Sciences from the University of Bonn, Germany, Masters in Agriculture from the University of Melbourne, Australia, and BSc in Agriculture with Horticulture major in the from the University of Philippines. Dr. Sonam is the editor-in-chief of the Bhutan Journal of Natural Resource Development and an editor for the International Journal of Environment. He also previously served as an associate editor for the official journal of the International Society of Organic Agriculture. He's a specialist in organic agriculture and a national task force member for the International Federation of Organic Agriculture Movements. Please welcome Dr. Sonam Tashi to present his topic on production and quality assessment of mycelium-based leathers from different mushroom species.
Thank you, Sring, for that kind introduction. Good afternoon and Kuzampola. Given the composition of the audience here, I'll try to tone down on the technical aspects of my presentation, and as and when possible or where relevant, I will explain some of the technical terms if I don't forget. Let's just to begin with, the mycelium here refers to fine network of threads and structures, which again technically is called hyphae. So again, I'll not go into the further details of the technicals of that. And the fungal species that we are referring to here are two different mushrooms. One is Ganoderma lucidum, which is reishi, and the other is Piloratus ostratus, which is oyster. So if you look at the figure on the right, there's a huge market for leather and leather products. Last year, the leather market was more than close to 500 billion USD, and this year is going to increase, and it will continue to increase in the future. That's the projection based on ABRC, or the compound annual growth rate of about 7%. And that goes to show that we love, except for the vegans, the leather. Because they're comfortable, they're durable, and versatile. You can use them not just as leather coats and boots and so on, but even in the automobiles, cars, aeronautics, and so on. And all our conventional leathers, or most of it, come from animal skins and hides. And that's where the problem starts. To get our leather, we have to raise animals, and hundreds of hectares of land in Amazon are being destroyed just to raise animals so that we can have our leathers, leather boots, leather shoes, wallets, and so on. And also, the animals generate a lot of waste, and in the process, there's also a lot of tons of greenhouse gas emitted. And that's just the first part. And during processing the leather in the tanneries, we use a lot of chemicals, harmful chemicals, which are again harmful to the factory workers there. They suffer from skin diseases, skin cancers, allergies, and so on. And then again, the effluents that go into the river, water, and the soil also impact the environment. And so, we see a major environmental, social, and ethical issues in producing leather, and particularly post-1970s because of sustainability movements. There's also concern in terms of sustainability. On the right, you see the mushroom that we produce in the lab from the mycelium, the fungus. Just a small sample here. And so now increasingly, these plant-based leathers are being kind of explored. Particularly, it's not to say that plant-based leathers were not there in the past. Centuries back, they had some plant-based leathers. But then these were not on a large scale or commercialized until the 2010 and 13. Now there are also a few fashion shows based on the leathers produced from plant-based, such as apples. We can produce leathers from apples, pineapple, bananas, coconuts, cactus, and so on. And so these plant-based leathers are considered to be more green, compassionate, and also they are eco-friendly. Of course, we have to be mindful of what treatments or the substances we use to treat the leather. And there have been a lot of studies to compare in terms of the quality, the comfort, and so on. And the leather being derived from plant-based is also doing quite well. And there are also quite a number of studies on leather being produced from Ganoderma lucidum, which is Ganodum, and then Pleurotus ostratus, that's our oyster, the common oyster, from mycelium of that. So mycelium, like I said, is this thin structure. It is actually a vegetative part of mushroom. And then the mushroom that we eat is the fruit, the reproductive part. So the mycelium is the vegetative part, and from there we get a mushroom, which is actually a fruit, fungal fruit, and also a reproductive part. So we had in this study 3 major objectives. One was to quantify and compare production metrics, such as fresh weight and moisture content of both these species in the lab. Second was to determine the effects of glycerol and ethylene glycol on tensile strength, apparent density, and water absorption capacity of mycelium, because these 3 parameters have implication on the quality and then the durability and the comfort and so on. And finally, determine the effects of citric acid as cross-linking agent on tensile strength as well as apparent density. So we come to the lab work here. First, of course, we produce the mycelium. I'll not run through the whole process of how we produce this leather in the lab, because then it will consume all of our 12 minutes. But then first we cultured, then we sterilized, then incubated, then pasteurized, incubated, and kind of harvested at the end. So it was almost like a 3-month process. Then after harvesting and producing the leather, we had this post-harvest treatment. So first we used glycerol and ethylene glycol. These are the plasticizer. Plasticizer is again a substance which is added to a material to soften, to increase the flexibility, and also reduce the brittleness. I don't think anyone of us would be interested to wear a stiff kind of leather jacket. And then this plasticizer does that by reducing the intermolecular forces and then allowing these molecules to move more easily. And then we use the third substance, the reagent, the cross-linker, which again is a technical term. Cross-linker actually helps to soften, also reduce the, increase the flexibility of the producer, and also the mechanical strength of the product. So these three materials were used at different concentrations now. So 0, 20, and 40 for glycerol and ethylene glycol. Yeah. 0 is, of course, the control. And for cross-linker, again, three concentrations, 0, 0.5, and 1.5%. Then some of the parameters that we measured. So obviously for the mycelium mat that we harvested, we looked at the yield and then the moisture content. Then for the leather, tensile strength, apparent density, water absorption property. The later two will not be presented here in the interest of time, but it's there in the whole article, manuscript. And of course, for the biomass and then the moisture content, we did independent sample t-test. And for the other three parameters, we had this factorial analysis. And of course, the standard 5% threshold was used for the statistical significance. That's for the natural science. For the clinical, they go to 1%, and for the social science, they go to 10%. But clinical science people, if the result is not significant, they increase to 5%. Anyway, there's a different thing to discuss later. So that's just to quickly illustrate the field, the lab work that were conducted, activities that were conducted. And here you see the, sorry, okay. Yeah, that's the leather, a few samples. Yeah, for the biomass, mean fresh weight of Ganoderma was significantly higher than the fresh weight of oyster. And this could be because of advanced metabolic machinery in Ganoderma. And the literatures also say that Ganoderma secrete a broad spectrum of extracellular enzymes which facilitate breakdown and assimilation of complex organic substrates. For the moisture content, we can see oyster or the Pleurotus had significantly higher than the Ganoderma. But this moisture content is basically much higher than what is required. If the moisture content is too high, then we'll have all this fungal and other growths. But basically, this is quite high. And the interspecific differences are likely attributable to inherent physiological and structural characteristics, including high field density, water retention capacity, and extracellular matrix composition. Further, we can also say the loosely packed hyphal arrangement and greater water binding components of Pleurotus may contribute to its higher overall moisture content. Now the effect of glycerol on tensile strength. So there was a significant interaction between fungal species and glycerol concentration on tensile strength. And we can also see for both the species, when we increase the concentration, the tensile strength gradually decreased. Particularly from 20 to 40, the decrease was very sharp. For the effect of ethylene glycol on tensile strength, significant interaction between fungal species and ethylene glycol concentration was observed. And you can see even in the illustration. So similar kind like earlier result. So I'll not again go into the details. Then finally the cross-linker, the effect on tensile strength. So no significant interaction between fungal species and citric acid concentration on tensile strength, but a significant main effect of citrus on acid concentration. Unlike the other two here, you see this tensile strength actually increasing. So finally, I'll summarize and make a short conclusion. So after producing the mycelium mat, we measured that as well as the moisture content And for the leather, we measured tensile strength, apparent density, and water absorption. And for the post-harvest treatment, we used ethylene glycol and glycerol as well as citric acid at different concentrations. Then our finding was Ganoderma produced significantly higher biomass than Pleurotus ostratus and exhibited lower moisture content. Treatments with ethylene glycol and glycerol reduced tensile strength, while my mouth is getting dry. You can have a little bit of water. Sorry. Sincere apologies. So yeah, basically we can read the summary and conclusions from there, but I just want to highlight the last point there. So for sustainable leather production as an alternative for the conventional leather, we can use fungal mycelium. Of course, it's proven there, but we are just trying to redo it, almost like reinventing, but we are trying to look at these different parameters. So with that, I would like to conclude. Yes, thank you.
Thank you, Dr. Sonam Tashi, for sharing your comparative study and its findings, highlighting a potential and a leather alternative that can, may, and will fulfill your consumerist needs. Dr. Sonam, by the way, is also a vegetarian, and therefore the study could also be closely aligned to his lifestyle choices and needs. And to move on to the next speaker, we now have Mr. Namge Wanchu, a graduate student from the College of Natural Resources, Royal University of Bhutan. Namge Wanchu is a forestry professional and an emerging geospatial specialist with a passion for harnessing GIS, remote sensing, and AI to solve pressing environmental challenges. With a strong academic foundation in forestry and hands-on field experience, he combines practical knowledge with cutting-edge technology to drive innovation in natural resource management. Let's welcome Namge Wanchu to speak on his topic, machine learning-based estimation of above ground biomass.
Thank you. Honorable Vice Chancellor, Ambassador, distinguished guests, scholars, scientists, policymakers, fellows, researchers, and all of the participants. All right, today we are tackling something pretty wild. We are going to talk about how scientists are now teaching AI to get this, weigh an entire forest from space. And why would they do that? Well, it's all about figuring out its most important superpower. How much carbon is it storing? It's fascinating stuff. So let's jump right in. So really, think about it. How do we weigh a forest? I mean, you can't just throw it on a giant scale. No. For decades, this has been a huge decade for researchers. So therefore, I embarked on this journey to apply machine learning in order to estimate biomass. So we all know that it is absolutely crucial for understanding climate change. But the methods for measuring all that carbon locked up in the trees have been, well, let's just say, they have been a bit old school. Yes, the traditional way was tough. I mean, you are talking about individual tree. You're talking about teams of people literally hiking up the mountains, deep into the woods, in the gorges, among the cliffs, wrapping D-base tapes around individual trees one by one. Sometimes they'd even have to cut them down just to get an accurate assessment. Super slow, crazy expensive, and you'd only get a tiny, tiny snapshot of the whole picture. But now we are on the verge of a new approach, the promise to flip all of this on its head. Okay, making it fast, automated, and best of all, you don't have to harm a single tree. So to really get how this works, yes, I know it sounds complicated. We need to know a term known as above ground biomass. So when I'm referring to biomass in this study, I will be referring to above ground biomass. It is just the total weight of everything that's alive in the forest and that is above the soil. So, you know, the trunks, the branches, the leaves, the whole shebang. I love this analogy. Think of it like a forest's carbon footprint, but in reverse. Instead of what's being put out, it's the direct measure of all the carbon that is being safely stored away. So, what is the secret sauce now? What's the big solution? Well, it's not just one thing. It's actually this incredible, incredible partnership between two amazing pieces of tech. We're talking about peering some very powerful eyes in the sky with a super smart artificial brain right here on the ground. So let's meet our tech duo. First, the eyes in the sky. They are the Sentinel-2A satellites that is constantly circling our planet. And they don't just take regular pictures. They see the world in what you call supercolors, special bands of light that are totally invisible to the human eye. Then you've got the brain. This is a machine learning model known as random forest. And we are going to think of it as our AI forest detective. Its whole job is to be trained to look at all that satellite data and find the hidden clues and pattern. Now, this isn't just some sci-fi theory. This is happening right now. We're going to dive into a fantastic real-world study that I got the opportunity to carry out in Kensen Community Forest, which is located in Hadzongkhakla. We took this exact technology and applied it to the incredible and incredibly rugged temperate forest of Ha. So yeah, this is where our AI gets its very real big case. So here's how we did it. Broken down into 4 pretty clear steps. Okay, step 1, the team, my team and I, we actually went out into the field, manually surveyed 99 different forest plots to get super accurate real world measurements, recording a total of 1,640 individual trees. This took us about a month to complete. This is what scientists call ground truth. It's the reality on the ground. Now step 2, we collect this geospatial data. Collect satellite images of those extracted same 99 plots. Step 3, now this is where the fun begins. I trained the AI by showing it both the sets of data, basically saying that, hey, AI, look, this is what the forest with this much biomass looks like from way up in the space. And finally, step 4, we set the train AI loose on the data for the entire forest and had it predicted the biomass everywhere else to build a complete map. So the big question is, how did our AI detective actually do on the job? Well, let's get into the results, because this is where the story gets really, really interesting. It's a tale of both incredible success and some unexpected struggles. These are some of the softwares and the methodology that I adopted in this study. So, what were the biggest clue our AI detective latched into? Well, you might think it was just some about how green forest looked. No, but actually, it was way more than that. The most important signals, it turns out, were from the short-wave infrared bands. Ooh, now that's a pretty jargon mula. Now, what are those good for? Detecting moisture levels in leaves. So get this, how wet a forest looks from space was one of the biggest telltale signs of how much life, how much biomass was actually packed on the ground. Kind of cool, right? And all right, so when we tested the model on the data, it already knew, the 99 points, 99 plots it trained on, it was an absolute rock star. It scored what's called an R square of 0.84. Now, for those of us who are not statisticians, that's really, really good. It basically means that the model could explain 84% of what's going on within the biomass. To put it simply, it's absolutely aced the practice test. So you can see the blue, the triangular, the blue in that diagram. So, but, and this is a big but. Here comes the twist. When the model has to face its final exam, the testing phase. When it was shown brand new data it had never seen before, the score plummeted. It dropped all the way down to 0.42. Just think about it for a second. It went from explaining 84% down to 42%. And the big question for me was why? I couldn't sleep for days. Well, the answer has a fancy name. Spectral saturation. But the idea is actually pretty simple. Think about it like a satellite looking down can easily tell the difference between, say, a concrete parking lot and a small park. No problem. And it can probably tell the small park from a much bigger forest. But when the forest gets super dense and lush, the satellite sensors gets overwhelmed. The signal just maxes out. It hits a point where it can't really tell the difference between a really, really dense forest and a ridiculously, unbelievably dense one. To the satellite's eye, they both just look maximum green. Okay, so this whole spectral saturation thing is a genuine hurdle for sure. But, and this is the most important part, it absolutely does not mean that the project was a failure. Not even close. Because even a map that's, moderately accurate is still a complete game changer for a country like Bhutan. It is the first time that we have ever had a carbon blueprint in Bhutan. So let's take a look at what the blueprint actually tells us. And here's the final output, the real prize. This is my baby. The AI that generated this incredibly detailed map, it shows that the biomass across this huge forest area ranges from around 48 tons per hectare, all the way up to 275. The yellow color that you see, these are the places having less biomass. And then the darker shade ones are the ones having greater biomass. But it's not just a bunch of numbers, no. It's a visual map that shows us exactly where the biggest carbon hotspots are. For anyone trying to manage and protect these forests, this is an unbelievably powerful tool to have. So let's zoom it out. Why does it matter in the grand scheme of things? Well, first of all, it gives us a scalable way to map forests in places that are almost impossible to get to on foot, like the Himalayan Bhutan. So if we visually inspect this map, you see in here, this is what it looks like on the ground, less biomass. In this place, this is what it looks like in the ground. And in those darker places, you will see the forest is actually like this. So this is what my model is predicting. This is what my baby is showing me. Now for a country like Bhutan, which is already famously carbon negative, and this is how we can prove to the world with hard data. It also makes the reporting for big international climate deals like the Paris Agreement way stronger. And you know what that does? It can even unlock opportunities to participate in global carbon markets. And I would like to sum it up by saying that this isn't just a one-time project. A one-time project for one forest. What me and my team have built is a framework, a recipe that can be scaled up and used in other similar mountain ecosystems. It's a tool that directly supports a country's climate goal. It's literally tuning satellite pictures into real climate action. And that really brings us to the final, pretty wonderful thought. We are getting incredibly good at seeing the climate impact of a forest from hundreds and hundreds of miles from up in the space. So the challenge isn't about measuring anymore. The real challenge is about what we do next. Now that we can see more clearly than ever just how valuable these amazing ecosystems are, how are we going to use that knowledge to make sure that we protect them? Thank you. Now, before I leave this stage, let me take this opportunity for gratitude to acknowledge all of the successful completion of this research would not have been possible without the generous support, guidance, and encouragement of numerous individuals and institutions. I extend my deepest gratitude to all who contributed to this endeavor. First and foremost, I am profoundly indebted to my research supervisor, Dr. Rienten Doji, whose expertise, insightful critics, and unwavering support were instrumental in shaping this study. Your rigorous feedback and intellectual guidance not only sharpened the quality of this work, but also elevated my academic growth. I am equally indebted to Dr. Bhagat Suberi for your invaluable recommendations and mentorship in navigating the complexities of field data analysis. My sincere thanks also goes to Dr. Ugendoji for your constructive discussions which helped me refine the methodological framework for this research. I acknowledge with gratitude the Royal University of Bhutan College of Natural Resources for providing the academic platform and resources essential for this research. My sincere appreciation extends to the Faculty of Forest Science for fostering an environment of intellectual growth and professional development. I am thankful to the National Land Commission Secretariat for granting me access to licensed ArcGIS Pro software, which was indispensable for spatial analysis. This study would not have been possible without the cooperation of Wansa village community, whose hospitality and support during my fieldwork were invaluable. And I am also deeply grateful to my colleagues, Mr. Shacha Doji, Mr. Wangdi Rixel, Mr. Sangitili Doji, Mr. Tsiltrim Zangpo, Mr. Nimatsring, and Mr. Karmolodi for their active participation and assistance during data collection. Finally, I owe my deepest appreciation to all those who contributed directly or indirectly to this work. Thank you. Lastly, I would also like to acknowledge my own efforts in preserving through the challenges of this research. The journey has been a testament to personal growth and resilience. This achievement is much yours as it is mine. Thank you. Yes, thank you.
Thank you, Namgye Wonchu, for your very interesting study on machine learning to study biomass and to study carbon blueprint. This is exactly the kind of direction that our students should be taking. And it is also clearly evident from the number of conference presentations in this conference format that this research is not only confined to the faculty members alone, and it is also evident from the way it is formatted. And therefore, it's a very encouraging and healthy sign, demonstrating a growing culture of inquiry among our young scholars, and then the strengthening of research-based learning, and then the commitment of our institutions to nurture the next generation of researchers and innovators. And then the conference is doing just that, so a round of applause to all our student presenters as well. Lasla. And with this, we now have the question and answer session. And for this, we have, and we'd like to invite on stage our moderator, Mr. Chime Rinzin, Country Director of WWF, and then the session speakers, Karma Sharaf, Jigme Tinle, Dr. Sonam Tashi, and Namgye Wonchu on stage. Thank you, La.
Hello? Yeah. So, can we start? Okay. Thank you so much for presentation. It was exhilarating, and of course, myself being a conservationist, it was, very good. I almost felt like, a conference where we are dealing a biodiversity business. We have on one hand carbon guy, on one hand we have leather guy, and of course biodiversity resources, which keeps on stacking, that I said will naturally help us build our natural capital assets. So thank you all for the wonderful presentation. I thought it was also engaging, and basically looking at the new science of how we approach conservation, how we approach biodiversity in the context of human development, as I said earlier, but also looking at the larger space of business. I think yesterday there was during the fireside discussion about what is the purpose of research? How do we connect research with industries? I think you already have some examples as to how this research is already showing a pathway towards that business model. So with this, I would like to request audience to kindly ask questions to any of the panelists, but I would like to request to state your name, your organization, and then to whom you are directing these questions. Over to the audience, please. Yeah, please, here, a gentleman.
Good afternoon.
Okay, first, second.
Yes. I'm Baldan Doji. I work for Royal University of Bhutan. So my question is regarding the eDNA. So first of all, we would like to acknowledge that Royal University of Bhutan, CNR, we are able to achieve the country's first eDNA lab. So while eDNA lab is being used to identify the species, so is there any possibility that this eDNA lab could be used, especially in crime scenes, to detect the suspect? So for now, especially during a crime scene, we hear that oftentimes that the DNA analysis is being done abroad, which delays the case and is costly as well. So if you could clarify this one as well. Thank you.
Please.
So firstly, why do we need eDNA lab, a specialist lab? Is because eDNA is also present in the air. So when we take the sample there and open it, if there is no eDNA lab, then the sample gets contaminated. So that's why when we enter the eDNA lab, we have to wear all those suits, cover the mouth. That's why we are not permitting anyone to enter the lab except for myself and when I train somebody. So with regards to this one, so eDNA can be used for anything, like it's for forensic, wildlife crime, because the DNA can be in your clothes also. So you can just swipe it and you can do it as well. And also it can be used for like detecting the zoonotic diseases in the water. And also like in agriculture, if you want to see the pollinators and all those things, you can also use for that. So I also have the equipment in my bag to check the pollinators if somebody is interested.
Very versatile, let's say, technology that extends beyond eDNA and what it can do in terms of not just biodiversity, but of course in the field of medical. That's what I'm hearing. Crime, that's very interesting. May I request, sir? Danala.
I'm Tash Gelson, educator, not a biologist, so my question would be rudimentary. I have two questions, one to Karma Sharap and Jigme Tilne, and other to Dr. Sonam. The first is to Karma and Jigme. It was an eye-opening to know something about eDNA. So in the process of your investigation, I was just curious to know if there is any possibility of discovering a new species through your study. That's one question. And to Dr. Sonam, US was regarding production of leather from mushroom. So is there a possibility of the otherwise, mushroom from leather, which will contribute to reduction in pollution and also increase in food chain, food supply?
Thank you very much for the question. So for eDNA, we need a database firstly. So if there is no database, then eDNA is useless. So that firstly, we have to create a lot of database, like collect the hair sample, blood, then sequence them and put in the database. Then only eDNA works. So if there is a lot of the database is enough in the databases, then if we somehow get a different sequence, then we can say that, okay, this could be a different species, but we need to find the species to confirm. So obviously not.
Can I, Dr. Sonam, please? Can you repeat question, sir?
Your study was regarding production of leather from mushroom. So I was saying, is there a possibility of otherwise producing mushroom from leather?
I have no idea about that, sorry.
Very honest and genuine answer. Yes, can I request any other question, please? Yes, Lob.
I'm Yezer, Dean of Research in these linkages from Sherabsa College. I'd like to direct my question to Mr. Nam Gawangchu, and he did very wonderful presentation as well as he has got very wonderful baby. So my question is, just is your assumption, I don't know you know or not, if you use a LiDAR technology, you know, light detection and range. So what will your result or accuracy of your result if you use such technology? But I don't in Bhutan such technology, they are not, but just you might be aware of that technology as well. So if you could highlight. Thank you.
Thank you so much for the question. Actually, it was addressed in the whole research. It is actually based on only optical. I used only optical imagery just to test whether optical imagery can be used to predict biomass, subsequently carbon and carbon dioxide equivalent. So from this research, what I found out is that optical imagery itself, it is not enough to define the structural complexity of our forest. Given that Bhutan is a mountainous terrain, undulating surface, so we have lots of structural heterogeneity. So in order to, the recommendation that came from this research is, as rightly pointed out by Sir, we need to incorporate structural variables. Multi-sensor fusion should be there in future works to quantify biomass, carbon dioxide equivalent, and so on. Thank you.
I'm Lungtin Jamso, College of Language and Culture Studies, Royal University of Bhutan. First of all, I congratulate everybody for that interesting presentation. My question rather goes to my friend Dr. Sonam. Very interesting, because I have changed my perception about mushroom. Before it appeared to be a source of food. Now I can see my cloth there. When you know, science explored the feasibility of producing leather from mushroom, I'm curious to know whether they have some evidence as to how many kgs of my mushroom will produce me a, material to provide a shirt. Is there any estimate as to how much of mushroom will produce a material that would give me a shirt?
Last, thank you. I knew Longten Lubi will ask me the questions and no. Yeah, actually there's some misunderstanding in Mevala, because when I said mushroom, it's not actually we are using that mushroom as the mycelium mat. So, and the vegetative part before they turn into mushroom. So maybe that also partly answers Lobengi's question that she gila. So yeah, and one of my recommendations was that what would be the costing, but because of limited time, I didn't actually provide that recommendation. So maybe future studies could focus on how much biomass would we require to produce a unit of a kilo of leather. And using this mycelium, of course, Ganoderma, oyster, as you know, they have this medicinal properties, more therapeutic properties. They have antioxidants and other phytochemicals or plant nutrients. And they also have this, we'll have that, we'll also derive that therapeutic benefits, anti-aging, anti-cancer, anti-inflammatory, this lash of the last.
I was just going to say the same thing, from having a medicinal mushroom tonic, which we drink every morning, to one day having a medicinal dress that, feeds us osmosis-wise. So can I request some more questions, please? Yes, sir.
Thank you, La. Mine would be also to Dr. Sonam. I thought this was very interesting presentation and very useful. We could, become, Bhutan could become rich because we have plenty of, mushrooms from where we can, from which we can produce plenty of leather, goods and then sell outside. My question is, through this process, is it not possible that you might be producing plastic rather than, leather? Because it involves the process of plasticization, as you mentioned. So how could you tell the difference between, the plasticization? My layman's thinking is a process that might produce plastic, layman's thought. And maybe you must be producing something like the materials such as synthetic rather than leather. How could you tell the difference?
Sorry, La, that's why earlier, thank you, La. Earlier when I said I will make my presentation a little bit less technical, La, because when I say plasticization, we will not be producing any plastics in Mibala. Plasticizer is that substance which is added to make the material softer, more flexible, and less brittle. And so there's no way that we would produce a plastic when you're doing this plasticization. It's just to reduce this tensile strength in Mibala. So we are adding, we can also have this bio-based plasticizer being added to process. So did I answer your question? So you need not worry about producing plastic that would contribute to this pollution.
Sorry, can I, my question was, how confident are you that you are producing leather rather than anything else? Because till now, traditionally, we know that leathers are produced from animal hides and, but how confident are you that you are producing leather out of mycelium?
So, because in the interest of time, again, although in the template we were given to present this literature review also, I removed that. There are plenty of literature with good evidence that we can produce leather from mycelium as well as other plant sources. And this has been commercialized, like I said, since 2013 in many countries now, plant-based ghee. But it has not come to this part of the world. But since it aligns very well with our GNHQ philosophy and sustainability, probably we could think of going into that. Of course, sourcing the raw material could be an issue in the beginning, but in Pamagasil, I understand that they produce pineapple on a large scale. And if you can also have sugarcane to have this consistent supply of raw materials throughout the year, then we can think of having this plant-based kind of leather, not necessarily from mycelium.
Thank you to all the presenters for an insightful presentation. My question to Karma is, how accurate is the eDNA technique? Did you encounter any instances of false positive and false negative in detecting species?
So, to be accurate, it depends on the database. It's the same answer like I said earlier. So, for mammals, large mammals and medium-sized mammals, we are having a very good database. For fish in Bhutan, currently database is not very good. So we are getting lots of false positives from there. But we are working really hard to create a database. So recently we have did like sequencing of 46 fish species.
So we are trying, and we have, together with WWF, Department of Forest, next year we are rolling out nationwide eDNA survey, and there also we want to create the part of project is we want to create a reference database first. So once that the reference database is good, then we will be really like successful. And also like false positive, when we are working in the lab, we have to be very careful. For example, if I work in the lab, if I am doing it really cleanly, and my friend enter into the lab, he is taking like, not caring and going inside, taking a lot of DNA from other, then it will be affecting me. Then the things he carried in will be in my samples. So that's why we have to be very careful. If we are careful, then it is you who will get satisfied. Yes, thanks.
Thank you. And next, my question to Professor Sonam is, in the process of creating leather from mushroom, you're using a lot of chemicals. So I was wondering about the environmental friendliness of producing leather from mushroom.
No, the plasticizers and then what you call the cross-linker that we use, except for ethylene glycol, others are non-toxic, very less, minimal, and like they're less harmful, both to the humans and the environment. But for the ethylene glycol, actually we couldn't get the substitute, which is polyethylene glycol. That is less harmful than the second plasticizer. So any bio-based, any plasticizer and cross-linker can be used. And it has been used in other plant-based leather production. So very less impact.
Thank you. And next, my question is to Namge. Why did you use only random forest? An ensemble technique would have really helped in improving R-square and overall accuracy of the model.
Hello. Thank you for the question. For this question, I should also go back to the literature. Literature also pertaining to the Himalayan range, because when we refer to literature, we should refer at the similar topography and similar climatic regions. So in all of these regions, yes, they have, in other regions, they have employed this technique in order to quantify biomass and carbon and so on. So when they did it, it was found out that random forest was the most efficient when it comes to optical imagery prediction. So therefore, I adopted this random forest model. Thank you.
Okay, thank you. Thank you for the wonderful answers. Thank you.
Can I see some more hands? Yes, gentleman there.
Hello. Okay. My name is Kildenzen, and I'm a research associate from RSTEM. So my question is to pertain to Dr. Sonam Tashi. And it's about the mushroom leather again. My question to doctor is about, like, I see that you guys are using the mushrooms as it is in the lab. Are there any plans in the future, like any gene modifications that is going to be done to the mushrooms, like gene silencing? Hello? Can you hear me? Sorry. My question is, like, are there any plans for gene modifications to be done to the mushrooms, like silencing the secondary metabolite productions to increase biomass productions, or using gene modifications to increase the mechanical strength or properties of the mushrooms? Like, after the advent of CRISPR-Cas9 technologies, we are able to, like, do large-scale genetic manipulations at a cheaper and more effective cost.
Yes, thank you for that very interesting question. Yes, that will be done in the future. Datudi, we don't have major plan along that direction. But if there are people interested, if there's funding, definitely. Yes, thank you. I hope you're not interested on that.
I think we can have last one or two questions, if there are any interested. Tasu? Tasu.
I just have one short question to Namge. Your presentation is very interesting, and I think has the methodology, the study that you've done has huge scope. I think, given that we are a carbon negative country, and it is important to find ways and means to stay carbon negative for as long as we can as a country. So just wondering, in terms of course, the mass of forestry in different locations as studied from space and through your whatever AI thing, it suggests that from that map we can see which places are dense in terms of forest coverage, which is itself very important because we can come up with measures for the less dense, I guess, areas. But I'm more curious about whether your study covers like which kind of tree species sequesters more carbon. If we have to do major forestation, what kind of trees we should be focusing on in terms of carbon sequestration, and which will help us in staying carbon negative. So if that was covered in your studies.
Thank you, Dashu, for this question. This is a very important question. Yes, in this research, optical imagery was used to explore the anila. And as I mentioned before, optical imagery has the limitation that it cannot detect the structural dynamics of the forest. So, in order to go to the species level, we need to have data from all of the dimensions. Since in layman's term, let's say optical imagery is a 2D model, so we cannot derive 3D model in order to classify the tree species specific. So in order to go for that, we in China and in Germany, they have done that species prediction. So this was done using LiDAR and SAR and also GPR, ground penetrating radar. And these were effectively used, and then the outcome was also very good. So the species level identification was out of the scope of this research. Yes, practical recommendations have been made to address and then to approach what Dashu VC's question and concerns for the future. So this study serves as a foundation so that others can develop based on this. So this is just a gist of anila. And then also the comparison that I showed with pictures of my map in my presentation, it is just a gist of what this map can do. The densities, we can correlate it with the basal diameters and then the tree height, so which can be effectively used in forest resource management. FMUs and then CDCL, they can use it effectively to to make their work more efficient. Thank you so much.
Thank you. I think we are almost out of questions. And before I hear the bell, I think it's good to close. But before closing, I just wanted to inform here by way of announcement, it's related to eDNA. WWF, together with CNR, ETH Zurich, Bhutan Trust Fund, we have been working on this global project, which has been approved. And we are, particularly WWF, we are envisioning Bhutan to be a regional hub of eDNA. So basically, Bhutan will serve as a service center to provide eDNA lab services for the regional countries. That's one. The challenges, as Sharad mentioned, is right now we don't have a reference database in Bhutan. So the sample has to be sent all the way to Zurich, where they process and match. The idea is also build that reference data, at least for the Himalayan region in Bhutan. So in February, if everything works out, we are planning to have a science policy forum, basically to discuss about eDNA, what the science behind is, but at the same time exploring what the application is of eDNA. As Karma mentioned, I think there's an opportunity to expand the application beyond biodiversity. It's about health, it's about other industries, but more importantly, I think it's also going to help Bhutan to help database that will help serve the region. So there's a big vision, at least from our partnership, but I'm sure it will also help in many other industrial opportunity, particularly GMC. You know, when we're talking about Gelifu mindfulness city, mindfulness in inverted comma, it's really about how do we, that mindfulness element, integrate and with larger environments. So I think this is a very promising technologies that will help us to keep track of our environmental indicators going forwards. So with this, I'd like to thank audience, and sometimes I think it's good to break for tea a little bit ahead of time. I'll be here once again with two other panelists, you know, who will be presenting a very interesting topic on the issues that is very dear to all of us as a national. I think it will be a very good presentation. I would hope everybody will be engaged as we had been just now. Thank you all.
Thank you to our moderator, Chimisa, and our presenters, Kama Sherab, Jimmy Tinley, Dr. Sonam Tashi, and Namge Wanchu for the very engaging and insightful discussions on the thematic area, and also to the audience for the very interesting questions that were posed to this team. With this, we conclude session 3, and this will be followed by a short tea break, after which we report at 3:40 p.m. And therefore, we request everybody to be on time so that we're able to wind up early and then leave early as well, if we can do that. And before you proceed to the tea, there's also a short announcement from the organizing team. If there's anybody in the audience that has lost your coffee mug, you can please collect it from us. Okay, la. With this, we'd like to thank you, and then you may proceed and then return to us at 3:40 p.m. La. Thank you. La. Good afternoon and welcome back from the tea to resume the 4th session. Since we're running slightly behind schedule, we would like to request our speakers to take note of it, and we will also like to submit that we'll begin. We know that many are missing, but we'd like to carry on now. We now have in this session Dr. Sherab Phunso. Dr. Sherab Phunso is an associate professor at the University of Technology, Sydney, with over 200 career publications and a 21 million Australian dollars career research funding in over 25 different projects. Dr. Sherab is an accomplished academic with global recognition for his pioneering works on novel membrane processes, nanocomposite membrane fabrication, desalination, wastewater treatment, resource recovery, circular economy, and on-site sanitation. Currently, his research interest is in green hydrogen generation technology. Dr. Sherab also worked for the erstwhile Department of Urban Development and Engineering Services at Thimphu for about 5 years. Please welcome Dr. Sherab to speak on the topic, resource recovery from wastewater, opportunities and challenges.
Thank you. First of all, I would like to thank the organizers RUB, Royal British Embassy, Canberra, and the DFAT for successfully organizing this conference. And I'm also very happy and then honored to be speaking here today in front of a lot of distinguished audience. I want to thank Dashaku Sab and the RUB for inviting me to this conference, and so it's fabulous to see so many people and to listen to so many people here. So before I start, I would like to acknowledge my mentor and collaborator, Professor Hok Young Sean. We did this work together that I'm going to present. So before I begin my presentation, just take liberty to briefly introduce my university. We've been talking a lot about the University of Sydney, so this is a little different. We are neighbors. So mine is University of Technology, Sydney, UTS. So it's a young university, and we have around 51,000 students, so 27% are international students. For some reasons, the universities in Sydney were not able to attract Bhutanese students, unlike other universities in Canberra, Brisbane, and Perth. And also we are ranked quite well in the world ranking, and also especially in water resources research, we are ranked quite high. So that's because that's relevant to my research. Again, you can see some of the other important milestones there. So we have many research centers and research center of excellence, and with the state-of-the-art research facilities, infrastructure. So you're welcome to come and join us anytime. So coming to my presentation, so this is where we are. We are, whatever product that we consume, we are in a linear economy. What it means is that we produce from the source, so we extract the mineral from this source, say maybe from the extraction, then we refine, produce, then we sell it, use, and then dispose it. That's what we call linear economy. And of course, with the environmental legislation, that we try to, so we try to have at least treat and dispose it. But now we're going beyond that. So that's why we're looking at a circular economy where we are trying to have a responsible consumption. So what we're doing here is try to prolong the lifespan of the product as much as possible by reusing at various stages, as you can see from this circle. And of course, at the final stage, when the product is no longer used, then we have to, of course, dispose it. But when you dispose it, we use the materials to recycle it back, and then so that's where we're trying to close the loop. So that's what we call the circular economy. So this is the model that we are looking at as a part of the resource conservation, not only to prevent pollution, but also to resource conservation, because we have only one planet, and our resources are limited. So we have to preserve it for the future generation as well. So the same way, my interest is in the fertilizer here. So the fertilizer production is also linear for the current linear economy. So what we do, the fertilizer production is really energy intensive. So so we produce fertilizer, then we use it and grow food, eat, and then becomes part of our waste, especially in the form of urine. And then we send it to the wastewater treatment plant in the form of wastewater. Again, here we put in a lot of energy to treat it, because otherwise we have a lot of this kind of problem, environmental problem. So this is what we are doing. Of course, the nitrogen is fine, but when it comes to phosphorus, the phosphorus is a finite resource. It's coming from the mining of the phosphorus rocks. So only few countries have that. For example, China, Morocco, Russia, and USA. So if these countries are controlling the supply of phosphorus fertilizer, then everyone is in problem. So that's a very high risk of the geopolitical issues. So that's why we're looking at how to have a circular economy for the nutrients, so that we don't have to depend on the fresh resources ever. So what we're doing here is we are trying to look at to bypass that. You don't have to send the nutrients to the wastewater treatment plant and spend a lot of energy to treat it or remove it, but then we use back it and recycle it and reuse the nutrients. So here we are looking at the urine, because urine has a more concentrated form of nutrients that I will see later. So in that way, what we do is we reduce the fertilizer, the fresh fertilizer demand, and also that we conserve the resource and also prevent the pollution. So that's the impact of the circular economy. So why urine? So urine is the major source of nutrient that's coming in the wastewater. So if you look at the bottom line here, there, so 80% of the nitrogen and 55% of the phosphorus that is present in the wastewater actually is coming from the urine. Even though if the urine by volume is only 1%, but it's containing the major source of nutrient. So what if we can separate this instead of mixing with water, separate this and then try to recover the nutrients from this urine. So why urine here? Because it has a lot of nutrients here. There's dissolved solids here, organics are there, the total salts which has calcium, magnesium, potassium, everything is there, and also urea. So fresh urine has a urea. So around 4, depending on you know the person, so 5 to 20 grams of nitrogen urea is there in per liter. But that's a fresh urine. But with the time, the urea will be hydrolyzed and then it becomes ammonia. So this is where ammonia is a volatile. Then that's why you get this very pungent characteristic smell of the urine. So that's the smell that you have from the urine is the ammonia. Please remember that. So here, if you look at, so there are various compositions as you can see, but our source is the nitrogen and phosphorus. Our focus is nitrogen and phosphorus here. So the research gaps here, we are trying to look at how we can recover fertilizer from the urine. But urine has been used as a fertilizer for a long time. This is the historical record. But here we can't use it these days as is this because of the health concerns and other environmental issues. So we need to treat that. But to treat that, there are a lot of gaps that research gaps that we need to be understood. There's a limited understanding of how the different microbial consortia is impacting the ammonia because we are trying to convert ammonia to a more stable form of we call it biological nitrification process. And also there's a lack of kinetic model, then there's a limited research how this ammonia and high concentration of other salts is impacting the biological process. And also there's a limited study on the economic impact or economic life cycle analysis, whether recovering urine is really a good idea. So we have a very big research aim here because this is a big project around 7 universities are involved, and then around 18 industries are involved. So the bigger picture is to transform the industry, wastewater industry into a circular economy at a larger scale, especially through urine source separation. So our part is actually the urine, but there are many groups who are working on different aspects. So say for example, biosolid and those sort of things. Okay. So here the objective is to how we can use the technology, we call it membrane bioreactor, so MBR, the membrane-based technology to treat the urine. And also how we understand the microbiology and the biochemistry involved in that, and then how can convert the urine into more concentrated form of nutrient, as you will see later. So this is the process diagram that we are following. So we have, say for example, waterless urinals that we collect urine, then store it in the tank, then from there we take it to the membrane bioreactor. So we set up as a reactor here, and then there is a membrane inside, and that is where the biological process happens. So that converts ammonia, which is very smelly, into nitrate. So which is after that we have a no smell the fertilizer. So we convert it into a liquid fertilizer. We call it as a URBAL. So URBAL means urine is valuable. That's the trait name that we have given, and so. And we can use this one as it is after this because it's highly sanitized. It is treated and there's no smell, and then you can even smell like this. We can do that even whenever there's visitors coming, so they can smell that. And also that it is filtered with the ultrafiltration. So there's no bacteria, nothing there. So that's quite safe to use it. So also you can further concentrate it using membrane distillation. It's another membrane process, but that depends on whether you want to ship the product to larger distance. So this is the product composition that we have. So we have around 3 to 9%, which is nitrogen concentration, and we have, I think I missed this one, but when we compare with the commercial fertilizer, it is quite higher in nitrogen and phosphorus concentration. So we have also tried this, sorry, I think I got to go back. Yeah, sorry. So where is it going? Sorry. Okay, so this was the first work that we've done, so this is to verify this, and then this is one of the students who work on this one, and we verified how the MBR and the MD can be, safely, this technology can be tested, and that it's worked really fine. So you can see this publication, and this this is also more work on the test. Different plants were tested, and with comparing with the commercial fertilizer, and in some cases even our urine fertilizer is much better than the commercial fertilizer. So also we have one of the issues with this is because of high ammonia concentration, high salinity of the urine, the biological process is very slow, so it takes very long time to, so it adds on the capital cost. So we want to reduce how much as possible. So that's why we are working on how it is impacting, and we still are trying to go beyond seven days of the HRT. This is called the hydraulic retention time. And then we put it several, say for example, biofilm carriers, or maybe sometimes we put this activated carbon so that we can provide more surface area for biology to grow. And we have been able to reduce around 40% or 60% hydraulic retention time. So which means we are getting there so that we become more efficient our process. So this is the same results we have here, so I don't have to present here. So the impact is that the downstream, how it is impacting, because when you divert the urine, then the wastewater treatment plant doesn't receive any nutrients. So their treatment costs significantly reduced because they don't have to remove the nitrogen, nutrients here. So this is, I will just, sorry. Yeah, this is the significance. Like it really, if you have this kind of a system, then you can reduce the capital cost. So that's a significant benefit for the utilities who are operating the plant, and also for the benefits for the society, because it's really contributing to the sustainability and also reduction to the environment, and also it creates new business opportunities. So here we have in Sydney a lot of new developments coming up, and then there's a lot of water recycling schemes coming up because they need to reduce water consumption. So when we have this water recycling together, then 50% of water can be reduced. And also we have opportunities where this urine diversion can also be introduced. Okay, so this is my group. So thank you very much for your time.
Thank you, Dr. Sharaf, for your very informative presentation on circular wastewater management, highlighting innovations in nutrient recovery, and demonstrating how sustainable approaches in the wastewater sector can address environmental challenges and the potential for collaborative research between Australia and UTS on that front as well. And with this, to move on to the next session speaker, which is also the last before the fireside chat, we have Bhaskar Sharma. Bhaskar Sharma is a lecturer and currently the head of department in the Department of Civil Engineering and Surveying at the Jimmy Namgyal Engineering College, Royal University of Bhutan. He was awarded an ITEC fellow to pursue master's degree in surface water hydrology at the Indian Institute of Technology, Roorkee, India. He has more than a decade of experience in academia and research, with primary research interests focusing on understanding hydroclimatic variables and flood dynamics in the context of climate change. His research includes environmental and sustainable studies, and he has published several research articles in the field of hydrology and climate change. Let's welcome Bhaskar Sharma to speak on his topic, Emission Reduction Potential of a Food Waste-Based Biogas Plant, Installation and Lessons Learned in Bhutan.
Good evening, everyone. So today, as a last speaker, so this is very pertinent issues in Bhutan, especially the waste. So I'll be talking how the food waste is contributing emissions, and this is the emission that is really causing the climate change. As pointed by the earlier speakers, we are already in carbon negative country, but that should not, make us naive, and we should pursue to reduce our emissions, because future there are a lot of progress happening, and then our country in the progress, as it progresses, there will be a lot of emissions, but we keep on trying to reduce our emissions and keep our country carbon negative. So with this, my topic is emission reduction potential of a food waste-based biogas plant, installation and lesson learned in Bhutan. Basically, I have modelings that has been done, and this work was supported by World Wildlife Fund, WWF, and also partly supported by National Environment Commission. So as I told you, Bhutan faces growing urban waste management issues, and that is recognized by everyone, and even the developed countries are facing it, let alone the developing countries. As per National Waste Inventory Survey in 2019, the urban household produces 0.7 kg per day of waste per day, and rural household, it produces 0.4 kgs of waste. So you can partly see how much the urban households are producing waste. With this survey, they also found out that 50% of the total waste in 2019 is actually a food waste. So this gives an idea how we can utilize this food waste and reduce emissions, because most of these emissions are happening from the organic matters. Particularly when it comes to greenhouse gases, methane is one of the most potent gas. So if you see greenhouse gases, the trajectory for the greenhouse gas developed by the Department of Energy and Climate Change. So in 2015, we have around 126.5 gigagrams of carbon dioxide equivalent, and it is projected to increase in 2030 and 2040 by almost 108%. So when I talk about greenhouse gas, the most potent gas in greenhouse gas is the methane. So it is 84 times more potent over a period of 20 years, and over a period of 100 years, it becomes 28 times more potent. For example, 1 kg of methane is equivalent to 84 kg of carbon dioxide. So impact of 1 kg methane is equivalent to 84 kg of carbon dioxide. So 30% of global increase in temperature is caused by methane gas. 16% of global greenhouse gas consists of methane only. And landfills are the third highest source. This is based on the USA, Imela. And landfill contains 21% of food waste. So 2.7% of greenhouse gas in emissions is attributed to waste sector. So one way of reducing this methane is to utilize food waste based biogas technology. Currently in Bhutan, we have cow dung based biogas plants. So mostly use cow dung, and the rural, this is mostly deployed in the rural part of the areas of Bhutan. My objective is to model these emissions from the food waste based using different scenarios. So particularly my objectives are quantify the emissions from landfill management practices, compare baseline emissions, so what is our current waste management practices, and compare with the fictitious management operational scenarios, evaluate how biogas can bring economic feasibility, whether this is economically viable or not, and to see what are the lessons learned from the a portable 1 ton per day biogas plant that was installed in our campus, Jiminamgel Engineering College. So all the literature suggests that this has potential. So a lot of developed countries has already been using this technology to produce clean from waste to energy solutions. So this is our study area. Our campus is in the Deothang, in Samzongkhar, and the plant is the biogas plant is installed in the campus. The distance from Samzongkhar to Deothang is 18 kilometers. So waste carrying vehicles has to move 18 kilometers up and down, so almost, so to reach our campus it is 20 kilometers to be precise. So waste carrying vehicles has to move 40 kilometers altogether. So research gap, till now, yes, of course, there are emission studies being done in Bhutan because as per IPCC greenhouse gas inventory, this is required for our nationally determined contributions 3.0. But life cycle assessment from the landfill management practices has not been done. Also, my scope of this research is, my sampling is only done at the landfills, it's not done at the households level. So this is the large methodology that I have used. So for this one, I am using emission quantification tool. As yesterday's presenter said, that not all models are wrong, but some are useful. Perhaps my model is useful. So, yeah, and I also did the economic analysis, whether adopting biogas really helps, really is it economically feasible? And I also had this different scenario modeling. So in business as usual, so that's what it's currently practiced. In scenario one, what I had is, we already had the biogas plant installed. So I put that parameters into my model with the biogas and see what is the emission. And second one, with same biogas, I also try to reduce the distance for the waste-faring vehicles. So, and try to see what are the emissions from these two scenarios. So this is from the result from our waste sampling. So this sampling is done at the landfill, not at the household level. So that's the scope, so I have to clarify. So from the landfill area, 15.86% is food waste. And the highest one is plastic and paper. So from Samjongkhar and Deothang combined, we have total waste of 2.7 tons per day of waste. From there, we have food waste 15%, so around almost half ton per day is food waste alone. So this is a result from our, as per business as usual, so current landfill management practices in Samjongkhar landfill. So based on this, methane is around 43.938 kilogram per ton of waste. When I convert all these methane, greenhouse gases and short-lived climate pollutant and convert that into total greenhouse gas emissions, carbon dioxide equivalent, we have around 1.2 tons of emissions, carbon dioxide emissions. So now in scenario one, when I have the biogas plant, along with transportation, because I have to ferry all the waste, food waste up to the biogas plant, again the vehicle has to go back to its original station. So with that, what I found is total, if you see the total greenhouse gas emission at the right side, it reduced by 14.5%, the total carbon dioxide equivalent. Similarly, in scenario 2, you will see reduction is 99%. So here, what the model suggests is, rather than the emissions happening from the waste, there is more emissions from the transportation. So that is what has been observed. So logistics and management itself is one of the issues rather than the waste itself, if you see in terms of emission. So overall emissions, you can see in scenario 1, slightly reduced, around 2.9 tons. If we utilize the scenario 2, we try to maintain the logistics of transporting the waste, then we can drastically reduce our carbon dioxide equivalent. So in discussion, so while we carried out this research, at the first point of time when we went for the sampling, the smell was horrible. So my friend even had headache for 3 days. He had to take medicine. So after sampling for 2 weeks, then everything was set. We had, in consultation with the environmental officers from the Thomde, they also cooperated with us. And for around 1 month, they continually supplied the food waste to our plant. After some time, the environmental officer informed me that the landfill is very clean, there is no smell. I also went there. So I verified, the landfill looks very, otherwise if you visit any landfill area, you'll have a headache if you visit it. So there I feel there is no odor in the landfill. So that was one good thing about implementing, using biogas. So as I said, more importantly, emissions from transportation has to be taken care than waste per se. So if you see our biogas, it's 1 ton per day. So potential is it will produce 80 meter cube of gas, remember? But actual production is happening is only, because we are feeding only 0.5 tons. That's our input, because that's the available food waste. So with that, only 34 meter cube per day was produced. But again, because of operational efficiencies, considering 70% operational efficiencies, we are able to get 24 meter cube per day. So that's, and if we convert that into calorific value, 1 LPG gas, it contains 14.2 kg. So in that 14.2 kg, we have energy of 653.2 million joules. So this is from 1 LPG gas. But from 24 meter cube per day, we have 508 million joules every day. So it's like 23 LPG cylinders per month. Our colleges, on an average, uses, in the student kitchen, uses 18 to 20 LPG cylinders on a monthly basis. If you are able to operate very efficiently, we can really offset the cost for the LPG gases. So lesson learned. Now, to be unfortunate, it's quite unfortunate that the biogas plant has become defunct because of, well, the technology is fine, but because of our own, all of us, remember, that has contributed. Because of our mindset, our attitude, we are not able to, yeah, I'll just, sorry, how I go back? Because of our mindset, we get food, although segregation is prioritized, even in Thimphu, even in Samjongkhar, even from the areas, food waste is, there is wet day and dry days. But even in wet food waste, there are metal spoons, napkins, there are spoons. This has really caused a problem to our biogas. These are directly fed, thinking that these are all segregated, and this has caused huge electromechanical issues. Our faculty at Department of Electrical Engineering technicians are working on these electromechanical issues. Right now it is under maintenance. That is, I would like to recommend that at least if there are any policymakers, environmental officers, segregation has to be done at the source. We have to be responsible in segregating our waste. So that is my key message to everyone. We are doing our part, but we as individuals should do our part as well. In order to effectively gain from biogas, we need to place biogas at a strategic point, because logistics plays a major role. So where do you place that? Because transportation itself is a biggest emission causing agent. We need very dedicated and trained professionals for operation, like somebody who has very good knowledge about the biology, who has very good knowledge about the chemistry. So those persons should be dealing with these types of and adequate additives, because sometimes there was not much methane yield. We run for 2 months, there was adequate methane, but the energy was not there. So problem was there was not much methane content, there was more carbon dioxide. So that, because there was not much organic reactions happening inside the digestate chamber. So in conclusion, yes, municipal waste is a greater concern, not just in our country, but most of the developing countries. There is inadequate waste management. Most of them are dumped at the landfill, although it is segregated at the urban areas, but ultimately it goes and dumped and mixed. There's making entire land management, waste management practices futile. So this quantifies greenhouse gas and short-lived climate pollution emissions at the landfill site. This also evaluates the potentials of biogas plant. Of course, if it is running at full capacity and running efficiently. Installation of biogas, minimizing transportation can significantly reduce carbon dioxide. May not be up to by 99%, but maybe up to 50%, even by 60%. That would be very helpful for the environment. So it also evaluates the economic feasibility of the gas. So yeah. And finally, this addresses, the entire study addresses our zero waste to 2030 policy. Thank you. Thank you.
Thank you, Mr. Bhaskar, for sharing valuable insights on biogas technology and its potential contribution to sustainable waste energy landscape, and also a reminder to other sectors in terms of your job responsibilities, including waste segregation. Now we are in the Q&A session for this session, and for which we would like to invite on stage Country Director for WWF, Sir Chimi, and also the session speakers, Dr. Sharaf Phunso and Bhaskar Sharma. And since we are really short on time, we would like to request the team to, as much as possible, to, how much are we giving? If we could entertain maybe for each of the sessions, maximum 2 questions, and then wind it up, to allow the fireside chat to come in. Thank you.
Okay. Thank you to both the speakers. I was really impressed with the idea of the waste that we generate can actually be plowed back into energy economy nexus. And we already won about the time. I would like to straight away go into the Q&A session. So if there are any questions, please.
My name is Tojuan Chu. I am a Dean of Research and Industrial Linkages at Paru College of Education. My question goes to Professor Sharaf Phunso. It's very impressive to listen to your talk. Instead of urine, I think we would recommend that your research include even feces, human feces. In the process of doing your research, I'm sure you also thought about the welfare of our country, Bhutan. So do you think that considering our Bhutanese belief systems, do you think that people would be motivated enough to use fertilizers which are made out of urine? I'm not sure whether I made it clear, but what I'm trying to say is whether you have considered those spiritual, religious, and then psychological perspectives of the end users. Thank you.
Okay, that's an excellent question. Thank you. To your first questions, I think feces, of course we focus on the urine treatment just now because, as I said earlier, the majority of the nutrients that's coming to the wastewater treatment plant is actually coming from the urine. So of course there's the feces there as well. So, but yeah, as I said, there are different groups who are working on that. So our focus was on the urine. To your second question about so that's the community acceptance, I think, that you're talking about. I think it's a challenge, still a challenge, even in Australia. I think, but in the last 10 years or so, people's, through education, awareness and all, I think there's a significant improvement in the people's perception and awareness about sustainability and the need to conserve the resources. So I think we did a couple of just informal surveys, and it's majority of the people seems to accept. But we don't have the in Australia, there's no legislation yet for this kind of fertilizer to be applied to the land, because you need a different kind of approval process. So we are working on that, but just now we got approval for hydroponic application. So hydroponic means you're not applying to the land, so we can use, but we're still limiting to non-edible plants. So we can apply this fertilizer in the lawn, gardens, or anything that we use in the parks and so forth, where we don't have to eat. So, but even if you eat, it's quite safe, because as I said, there's no virus, there's no bacteria there, because it's highly treated, high quality treated fertilizer. So I think, but when it comes to the spiritual things and well, yeah, I would say that it will take time, but yeah, it depends on the people's education and awareness. But if sustainability has to take over, yeah, I think we have to eat. Thank you.
Can I have question? Please. Mike, please, in the front row.
Hello, my name is Vicky Bannerman. I'm from ECU, Edith Cowan University in Perth. I want to focus my question on you, Mr. Sharma, because how do you think, or what strategies do you think you need to put in place to encourage people to sort their waste? Because, you know, we're through that program at the moment. We have 3 different bins that people can put their waste in. But it doesn't always, they don't always put in the right bin, but there are 3 bins there. But how do you encourage people here in Bhutan to do that? And what sort of strategies would you need to put in place to make that happen? Thank
you. Thank you for the question. To encourage people is very difficult. That motivation has to come from within. If you want to save your country, save your environment, that has to come from you within. Yes, government is doing their part with all this awareness program, with educations, but in one way or the other we are lacking that sense. Sometimes if you travel along, there are people who just naively throw out their water bottles from their cars, and those cars are like Fortuner, you know, Toyota Fortuners. You see the mentality, you know? Those are highly educated, I presume, and let alone those who are illiterate, you know. So yes, government is doing their part on their creating awareness and giving the education, and but these things should come, that encouragement and motivation should come from within. That's what I say. If you have any better answers.
Can I request question?
My name is Senchu Suring. I'm principal of USLink Higher Secondary School, but today I'm here as a representative of Edu+. Thank you very much for the presenters. In the era where we are struggling with the energy crisis, it's good to know that our waste is a very good source of energy if we use it properly. And also, I would like to mention that I do not come from a science background, so at times my question might be sounding very naive. Mr. Vaskar, your topic said emission reduction. So all the while I was listening with that mentality, it's something to do with the emission reduction. But towards your conclusions part, you said there has to be some additive to increase the production of methane. And I was saying, all the while we are saying methane is dangerous, and suddenly, just for the biogas, we want to increase methane, so I'm completely lost. Please throw some light. Thank you.
Thank you. I hope this is the same with everyone. So the methane, if it's not gone to the biogas, it's directly gone to the air. Now when it goes to the biogas, it is burning, it gets burned. So it doesn't go into the environment. It does not get released in the environment. That's the thing. So in order to increase the yield of the methane, we need to increase the surface area for the bacteria inside the digestate chamber. So that's why we need to add those additives. So that's what the literature suggests, because we were trying to see how to increase the methane, because the methane production was not much as what the manual says. So we are almost short by 30–40% down. So we are trying to see what could be done. So, and another thing was just sharing this, because this is a methane issues coming out. We had an issue of seasonal food waste. The biogas plant that is installed is German made, and the German guy, he told me that biogas is like your own gut. Treat it like how you treat your stomach. No? You don't want to feed it with all the junk and get acidity and gas and bloating. So that's same thing with the biogas. So once in a while in December and January time, there was too much input of orange peels. So that is acidic in nature. So that killed all our effort. It killed all our bacteria, good bacteria that are there in the, and again, for 2 months, again, had to feed with cow dung, because cow dung contains good bacteria. So again, we had to wait for 2 months to get that bacteria going. Thanks. Thank you.
Any more questions? Last, second row. And then maybe I'll take one question, then try to close this session, because there is, colleagues from next sessions who...
Hello. Kusu Sampula. My name is Sanam Toge, and I'm from the office of RSTEM. My question is to Mr. Vaskar. You have mentioned that the installation of biogas plant has led to the reduction of the odor from that landfill. So the residents of Thimphu, we all know that on the way to Memelakang to the Dochula, there is like a odor, like a very bad stench coming from that area. So would you recommend installation of biogas plant there, or are there any other alternatives to reducing that smell? Thank you.
Thank you for the question. Just last June, SAC Development Fund and Bhutan Ecological Society and Bhutan Trust Fund, collaboratively, they are installing 20 ton per day biogas plant. That's also, I think, portable one. So I do not know where they intend to place this, but I foresee the same challenges. So how they are going to, so maybe these challenges could be taken at the initial stage itself. If there are anyone relevant person, they can take this message. So I see these challenges. Yes, Memelecha maybe, odor may be there. This odor, methane in itself is odorless. If you see the, and LPG gas is also odorless. But the one that in the kitchen that we use, the odor is added so that whenever there is a leakage, you can detect with your nose. No? That is your natural sensor. So yeah. Thank you.
Last question. Okay, last.
Good afternoon. My name is Sonam Paljan, and I'm a student at the College of Natural Resources. So my question is also to Mr. Vaskar. I have heard of manure being converted into biogas, but it's my first time hearing food waste being converted to biogas. So as per my understanding, not only methane, but nitrogen also has a global warming potential. To be exact, it has about 298 times more potential than carbon dioxide. So sir have mentioned the use of carbon dioxide, methane to biogas. So what does sir have any recommendation about nitrogen being converted to any other useful resources so that we can minimize the global warming potential? Thank you.
Thank you for the questions. Biogas consists 50%, 60% is methane, and remaining is mixture of all other gases, including I have talked about short-lived climate pollutants. Short-lived, it is black carbon also, it is nitrous oxide, hydrogen sulfide, there are other components. I'm not very sure because the the percentage of nitrous is very less. If you happen to see in this one, it's very less generation, but I do not know how we convert, because in order to convert, you need to have hydrocarbon. Methane is a hydrocarbon which can burn. Nitrous is not a hydrocarbon, so it may not burn. So, yeah, I'm not a chemist, so that's just my knowledge. Thank you.
So with this, thank you so much. Like I said earlier, waste is a national issue. I think it has been very close to our leadership. There has been many effort in the past. There is still an ongoing effort, but biggest challenge that I've seen through the experience of biogas in Deotang and other initiative is ourselves. I think our behavior needs to change if we really want to address the issue of waste. That's one. Again, is waste in Bhutan urban issue or rural issues? For me, it seems more like urban issues where we have more literate people than the rural areas where they don't have the kind of education that we have. So perhaps that speaks to how insensitives that we are in urban areas as illiterate individuals. So I think there's a bit of questions that we need to ask when we discuss about waste and how we resolve the waste issues. So with this, I really want to thank again RUB, the panelists here, and of course Ambassador and Vice Chancellors and all other colleagues for being here. I hope I did my justice. This is my first time moderating a session, so it has been a steep learning curve for me as well. Thank you all.